All right, how's it going? This is our last week of discrete structures. It's very exciting. So, any questions? Did anybody solve the halting problem over the weekend? No? So after class, I made one comment on the halting problem, which is consider the ramifications if you could solve the halting problem. So the idea is you can write a C program and give it to this magic program that analyzes the code and tells you whether or not this program will exit at some point. And it will tell you in a finite amount of time. It might be long, but it will come back with an answer, yes or no. So imagine you take PA2, your Goldbach's conjecture problem, and you modify it so that it simply keeps trying to write even numbers as sums of primes, and if it ever finds a number that it can't do that for, it exits. Now you just hand this to your program and analyze it and say, does this program ever exit? And if it says yes, you know Goldbach's conjecture is false. You don't know what the number is, but you know that there's a counterexample somewhere. So you could do all kinds of amazing things with this kind of analytical program. And that's one reason most people have a pretty easy time believing that this is an unsolvable problem. And it's been proven for decades. It's been known for decades that it's unsolvable. All right. So let me switch gears now, and for our last week, we're going to talk about graph theory. And we'll touch on some of this in 223, probably. We'll code some of these algorithms, so we'll do a rehash of graph theory, but it's a subject I want you to have seen, at least in this course, ahead of time, and you'll encounter it throughout computer science as you go forward. So what is a graph? Formally, we can think of a graph as a pair of sets V and E, where the set V contains what we call vertices, and the set E contains what we call edges. And the set of vertices cannot be empty. You need at least one vertex to have a graph, but you don't need to have any edges. An edge has one or two endpoints. And the endpoints are vertices, so they're elements of V. And we say that an edge connects its endpoints. And by the way, if you're watching this video, I'm trying a new recording system here, so I don't know if the sound's going to come out horrible or weird things like that, but I think I've got it to where it's pretty good, but let me know. Okay, so what's a graph typically look like? Well, you draw some dots and you connect them together. There's a graph, has 3 vertices and 2 edges. There's another graph, we call this particular graph a cycle. Here's another graph, we call this graph a wheel. It kind of looks like a lopsided wheel. This is also a graph containing just a single point, a single vertex. Here's a graph containing 3 vertices, that's perfectly fine. This whole thing, these 3 vertices and these 5 vertices with these, that whole thing is a single graph. It's not what we call a connected graph because there's pieces to it. We can't get from this vertex to any of these vertices. But we still consider a graph to just be a collection of vertices and edges. So this is perfectly valid, as is this, as is this. Okay, so it's a very general concept. This is also a graph. right? There's nothing in our basic notion of a graph, a set of vertices with edges connecting vertices together. There's nothing about this that violates that, right? But this clearly looks kind of funky because we have multiple edges between the same pair of vertices. So we're mostly going to stick with connected graphs where everything is sort of in one piece. You can get from any vertex to any other vertex. And we're also going to stick with simple graphs. So in a simple graph, there is at most one edge between any pair of vertices. And remember, both endpoints of an edge could be the same, so this is still a valid graph. And this is not a simple graph, because there's actually two edges connecting this point to itself. And so what's an example of a graph? Well, computer networks come to mind pretty quickly. So here might be Netflix, the origin of all computer networking. So there's Netflix, and they might have connections to their 3 customers, or maybe to 3 servers, and those servers might farm out to multiple customers, and there might be some redundancy here. And so we can ask questions like, suppose that the connection from this server to this customer gets cut. Suppose we remove that edge. Is there still a connection between this vertex and the customer vertex? And there is. It can go through this middle server. But by drawing graphs associated with things like physical networks or electronic circuits or flow within a program or communication among a set of parallel tasks in a multiprocessor, by drawing graphs associated to these structures, we can analyze the graphs and make conclusions about the corresponding structures. Another common example of a graph is a map. Right, if you draw a map of campus, you can draw your buildings, and you can show which buildings you can go directly from and to. And this might be the STEM building over here, and we can get to the T building. But pretty much anything else that we want to do, we're going to have to go over to Geyser Hall and then walk from there, because otherwise you're walking down Fort Vancouver way. But then there's all these buildings that are connected to each other. Or you could do roadways or whatever. So it's also possible to have a directed graph where we have a notion of direction on each of these edges. And this might be the case if you were making a map of Portland, where everything seems to be a one-way road. And you can get from here to here, but you can't go in the other direction directly. You've got to travel around some other loop. So, so directed graphs are another variation. All right, some more definitions. 2 vertices are said to be adjacent if they're connected by an edge. So let's say 2 vertices, V1 and V2, are adjacent if they're connected by an edge. Let's call the edge E. We can also say E connects V1 and V2. We can also say E is incident to V1 and V2. And these definitions will be useful when we start trying to look at ways to store the representation of a graph inside a computer. We'll talk about incidence matrices, for example. So an edge is incident to the vertices that it connects to. And we can also say the edge connects. And we can say two vertices are adjacent if they're connected by an edge. And our two main representations will be an adjacency matrix or an incidence matrix. So we'll see that shortly. All right. More definitions. We always start off with lots of definitions when we start a new topic. So N of V is called the neighborhood of V. And it's the set of all vertices that are connected to U. Sorry, connected to V. Yeah. So the neighborhood of B would consist of A, C, E, and F. The neighborhood of A would just be the vertex B. And we can also say B is a neighbor of A. Just means it's adjacent to it. So the neighborhood is a set of all vertices that are your neighbor. All right, so here's our best definition. The degree of a vertex, and we can write either DEG of V, or sometimes we write the little hunchback D, the delta symbol V. This equals the number of edges that are incident to the vertex. So the degree of vertex E is what? How many edges are incident to E? 2. How about the degree of vertex C? 3. And B?
4.
And A? 1. Okay, so just the number of edges incident to it. And there's a detail here. Loops count twice. So if I do something like this, the degree of E is now equal to 3. So you kind of count, sorry, it's 4. So it's 1 edge, 2 edge, but this is a single edge, but you count it twice because it's beginning and ending at E. That's going to make things work out nicely. So let's look at this graph. So this is a graph with vertices and edges. How many vertices do we have? What's the cardinality of the set V of vertices? 6. And how many edges do we have? You can do this.
6. Oh, edges. I'm sorry.
Edges.
6 vertices. 8, 9.
I'll buy 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So here's a cool little factoid. The degree of this vertex is 2. The degree of this vertex is 3. The degree of this vertex is 3. The degree of this is 4. The degree of this is 3. And the degree of this is 3. So let's take the sum over all vertices of the degree of that vertex. 3 plus 3 is 6, 9, 12, 14 plus 4 is 18. And that's exactly twice the number of edges. And this is always going to be the case. So this is a theorem. So if you add up the degrees of all the vertices, you get exactly twice the number of edges. And this is why we want things like this to have degree 2. Because if it only had degree 1, then this would break. That's not the reason, but it's a reason to believe that this is a good definition. So why should this be true? Why should adding up the degrees always give us twice the number of edges?
Because when you count the degree of each one, you're counting essentially all the edges twice, because you're counting it once from one end and once from the other end.
Right.
When you're at the other vertex.
Yeah.
Because you don't have an edge that doesn't connect to another vertex.
Exactly. Every edge has to be connected to 2 vertices. And so if I draw another edge here, wherever I start from, the degree is going to increase by 1. Wherever I end, the degree is also going to increase by 1. This sum is going to increase by 2. And it doesn't matter if I go here or back to the beginning or wherever. How would you prove that formally?
So I'm thinking, like, the first thing that comes to mind is mathematical induction, but I feel like there might be a problem with that, because that doesn't necessarily prove that it can't be anything else. You know?
Mathematical induction on the number of edges will probably work though. Right? Because if we know that with a certain number of edges this formula holds, we can do what we just did. We could say add one more edge. Whatever vertex it starts at, the degree goes up by 1. Whatever vertex it ends at, the degree goes up by 1. And the number of edges has gone up by 1. So you can show if this holds for n edges, it holds for n plus 1 edges. You show a base case, which is 0 edges, and you're done. So mathematical induction will always be your friend. So with this result, we have a corollary. A graph can't have an odd number of vertices with odd degree. Any graph, if you look at the number of vertices with an odd degree, it's got to be an even number of vertices. So you cannot have a graph with a single vertex of odd degree, or 3 vertices of odd degree. It could have 2, it could have 4, it could have none. Why is this corollary true? What if we had a graph with a single vertex of odd degree?
Some of the degrees wouldn't be an even number.
The sum of the degrees would not be an even number. Because we know when we add even numbers together, we get an even number. When we add an even and an odd, we get an odd. If we have 2 odds and we add them, we get an even. Right? So we could write the degree in terms of what it's congruent to modulo 2. The vertices with even degrees are congruent to 0. The vertices with odd degree are congruent to 1. If we have an odd number of 1s that we sum together, the result is going to be odd. But we know 2 times the number of edges is always going to be congruent to 0. It's even. So straight modular arithmetic or even and odd facts tell us that the number of vertices with odd degree has to be even. Otherwise that rule breaks. All right, so what about directed graphs? So we have things like this, where there's a sense of direction to each edge. So we can still say U is adjacent to V, and we can say V is adjacent to U. But we say U is the initial vertex, and V is the terminal vertex. And we embellish our notion of degree So here's a fancier looking graph. We've got directions on these edges. So we just describe 2 kinds of degrees, an in degree and an out degree. So in degree is the degree of the number of edges going into the vertex. So we can write this as degree minus sign with the vertex equals the number of edges going into V. And the out degree is degree plus, and that's the number of edges leaving V. So if we look at U, the out degree is equal to 2, the in degree is equal to 0. What about V? What's the out degree?
1.
And the in degree?
2.
one more and then I'll do the rest. What's the out degree of x? 1, 2, 3. And the in degree?
2.
2. 1, 2. All right, you got it. I'll do the easy ones. So out degree is 1, and the in degree is 1, 2, 3. All right, so here's our theorem. So if you add up the in degrees, you get the same as if you add up the out degrees, which is the same as the number of edges. So let's see if that works. So in out degrees, 2, 3, 6, 7, 8. In degrees, 0, 2, 4, 5, 8. Number of edges, 1, 2, 3, 4, 5, 6, 7, 8. Math works. And if this was an undirected graph, you get that previous theorem directly from this, because we don't differentiate between in degree and out degree. So if we get rid of the arrows and we add up the total degree, it's just going to be the sum of this and this, which is twice the number of edges. All right, is this making sense so far? So let's make a dictionary of some graphs that we're going to encounter. So the first is called a complete graph. And this is written K sub n. And this is just a completely connected graph. Connections from every vertex to every other vertex. So K1 is just that. K2 is that. K3 is this. K4 is this. And so on. Cycles is C sub n. And this is just n vertices connected in a chain. So C3 is the same as K3. C4 is that. C5 is 5-sided. And so on. And then a wheel, Wn, this is Cn plus an extra point in the middle. So W3 looks like the 3-vertex cycle, but with an extra vertex connected to everything. W4 is going to look like K4. It's a wheel with an extra point in the middle. No, it's not K4. It's got a vertex here. And W5 is a 5-point cycle with a point in the middle. And so on.
So I just want to be clear, W4 and K4 are fundamentally different?
Yeah, so K4, these edges, I drew them crossing, but they don't meet in the middle. So could have done it like this. to see it. All right, so I haven't said this explicitly yet, but it should be looking pretty clear that this graph is the same thing as this graph and is the same thing as this graph. The way we draw this on the page is pretty much irrelevant. The only thing that matters is how many vertices do you have, how many edges do you have, and how do the edges connect the vertices together. And if I call this A, B, C, and I call this W, X, Y, they're still the same graph. Okay, the names we give to the vertices or the edges is irrelevant. So we can think of these things as being points connected to the rubber bands, maybe, where we can move them around, we can twist them, we can stretch them, we can shrink them, but we can't break them. We're not allowed to cut one of the connections. We're not allowed to add extra connections, but you can morph it around and change its shape, and as long as you haven't broken anything or added anything, it's still the same graph. Okay, and this is a recurring theme in mathematics, this idea of things that are essentially the same even though they look different. So we'll talk about terms like isomorphisms or homomorphisms or homeomorphisms, things that have similar shape or similar structure, but may appear different. So the classic example in topology, a coffee cup and a donut are basically isomorphic, because you could take a donut and you could squish down one side and you could pull out this side and then you could mash down the stuff to make a cup shape in it. But as long as you don't break it, it's still the same shape, right? Now, if you were to tear the clay you're using and open up this handle, then it's no longer homeomorphic to a coffee cup. Now it looks like a sphere or a disc. So this is part of a more general theme. All right, so there's a notion of a subgraph. So we can have another graph, W and F, and we can say this is a subgraph of VE if W is a subset of V and F is a subset of E. So here's a graph we were picking on before. All right, that's a subgraph because it contains these vertices and it contains these edges. But if I add something else in here, right, it's no longer a subgraph because this is not part of that graph. So one way we can construct subgraphs is by taking a graph and removing edges. So we can have G which is a set of vertices and edges, removing an edge. Gives us a new graph. So G minus, let's not use set notation, G minus that edge. Well, it's just the same set of vertices, but it's E with that one edge removed. So complement of that edge in E. And we can always do that, right? We can have a graph here. And if I want to remove an edge, just remove it. And you get a subgraph. Another thing we can do is contract an edge. And when we contract an edge, we remove the edge, but we take the two vertices it was connected to and we make them a single vertex. So for example, here's A, B, C, D, E. So if we want to contract this edge, we're going to remove it and we're going to make this vertex and this vertex the same. So we'll have A going to, we'll call it B prime, and C, and D. And then D used to connect to E, now it's just going to connect here. And B used to connect to E, it's going to connect there. So there's a contraction of this edge. And that's not a subgraph. Okay, we've taken an edge and sort of brought together its endpoints. All right, we can also remove a vertex. And if we remove a vertex, remember edges need to be connected to something on both ends of the edge. So if we simply remove a vertex, we've got to do something with the edges. And our trick is going to be just remove the incident edges. So also remove incident edges. So if we want to remove the vertex D, we keep everything intact except anything that was connected to D, and we get rid of those. So we lose those three edges. All right, so computer science time. So storing graphs. So how can we represent this kind of graph information inside a computer? Because we're going to want to analyze and manipulate these graphs using various algorithms. So we need a good way to represent them internally. And there's at least 3 different approaches we can use. So the first idea is what's called an adjacency list. So let me make a good sample graph here. I feel like all my graphs end up looking the same, no matter how hard I try. All right, there's a different one. So an adjacency list, basically, you list a vertex and then you list all the vertices that are adjacent to it. So it would be something like this. A is adjacent to B, C, and D. B is adjacent to A and E. C is adjacent to just A. D is adjacent to A and E. And E is adjacent to B and D. So how could we code that inside a computer? What kind of structure might we use? Linked list. That would probably be the first choice. Because we don't know how big these lists are. Now you could make a big array and blow most of the space, right? But this is what linked lists are for. So we could have a linked list. Each vertex would correspond to the start of a list, and the elements of the list would be the adjacent vertices.
Could you use a try?
You could. I think if you were naming these vertices like we're doing here, then a try starts to make a lot of sense. But if they're just being indexed with numbers, then probably try would be overkill. But if you wanted to maintain information about the vertices with, say, customer names or something like that, this could be an interesting application for a try.
So if it was just a shape, you probably wouldn't want to use one, but if it was like a map, like location names or something?
Yeah, if you had city names or something like that, then that might get interesting.
And classes.
Yeah. All right, so that's one approach. Second approach is what we call an incidence matrix. And so this is a matrix where on one axis we have vertices, and on the other axis we have edges. So let's go ahead and label our edges. We'll call this E1, bless you, E2, E3, E4, E5. So we'll put our edges across here. And vertices vertically. That worked out well. And now we just list which edges are incident to which vertices. So E1 is incident to A and B, and nothing else. E2 is incident to B and E. E3 is D and E. E4 is A and D. And E5 is A and C.
I imagine the code to use either of those two would be similar, because looking at it, you just have A. I guess it is a bit different because you're counting edges.
It's a bit different. For example, if you wanted to find the degree of a vertex, in this case we could move across and add up how many edges are incident to it.
Mm-hmm.
So this would tell us A had a degree of 3. In this case, we would look at the length of the list. All right, third approach is an adjacency matrix. And this is similar to the incidence matrix, but we just store vertices on both axes. So A, B, C, D, E. A, B, C, D, E. So A is adjacent to B, and C, and D. B is adjacent to A and E. C is adjacent to only A. D is adjacent to A and E. And E is adjacent to B and D. So there's an adjacency matrix. So different ways of representing exactly the same information. right? We can reconstruct the essential information about a graph from any of these representations. And depending on what kind of algorithm you're doing, you may be very interested in, for example, following a path from one vertex to another. In which case I could start with A and I could say that's connected to E1 and E1 is connected to B, right? And I could follow multiples like that. Or we may be interested in finding the degree of a node, a vertex, in which case we can just add across rows or columns in the adjacency matrix or rows in the incidence matrix. Yeah?
Something interesting that I noticed though is that they kind of create binary numbers too.
They do.
So
In this case, yeah.
So you could possibly catalog shapes based on numbers.
Yeah, you could. Which would be interesting. They don't have to always be binary though. So we're dealing with simple graphs, but if we had something like another edge connecting two vertices, we might have a number bigger than 1. This could represent the number of edges connecting one to another. We can also do directed graphs in any of these. So in a directed graph, this might be viewed as from and to. And so a 1 would mean we were coming from A to B, right? And BA might be a 0 if we're not also going from B to A. And we're going to eventually talk about weighted graphs, where we associate not just the fact that there's an edge, but a weight or a cost associated with that edge. And in that case, we could actually store the weight of an edge in here also. So if we were doing something like a city map, where this had, where each edge had a certain distance associated with it or a certain toll associated with it, we could store that information inside here. And it could be positive or it could be negative in some cases.
Is that possibly part of how GPSs work? Like when directing?
Yeah, we'll get into some mapping type algorithms, particularly something called Dijkstra's algorithm, which lets you find shortest paths based on constraints, how expensive it is to travel along an edge. And in some cases, that's a very easy task. In some cases, it's very complex.
So is it like reasonable to make something like an adjacency list but use edges?
Let's see. I don't know if that would get you all the information. So we could say E1 and E2 are connected.
No, I guess that would, yeah.
Well,
That's true.
that might. Yeah, but then if E3 and E2 are connected, we wouldn't know if they were connected at the same point. But it is interesting that we can get away with just vertices, or vertices and edges. I wonder if there's a way to do it with just edges. It's a cool question. It's a good non-graded homework question to work on. All right, so we'll talk tomorrow about isomorphisms of graphs, looking at when two graphs are effectively the same, and ways to determine that. And then we'll start talking about paths, moving from one vertex to another. And that's going to lead us to eventually looking at algorithms for finding shortest paths from one point to another. All right, so we'll start with that tomorrow.